In the last video, we talked about using SSH to connect to a remote system. In this one, we'll go through an example of how that system might be structured. I'll use the Ohio Supercomputer Center, or OSC, as an example. And so while some of the concepts can be extended to a number of other HPC systems, the details are specifically for OSC. Here, I've put together a diagram that represents at least my understanding of how that system is structured. We'll talk through this a piece at a time and refer back to this diagram as a reference as we move through future videos. First, we have our local computer, the one we're physically working on, down here in the bottom left corner. And the dotted line indicates the connection we make from that computer to the remote system, likely through SSH like in the last video. In this case, the connection is actually made to a specific set of nodes called the login nodes. Now, before we go any farther, let's deal with some terminology. The terms nodes, cores, and processors will get used a lot. Let's deal with nodes first. A good way to think of a node is as the physical box that makes up the computer. For a desktop computer, think of it as the computer tower. Contrast that with cores, which is interchangeable with processors. For example, I can think of my laptop as a single node that has 4 processors, and a desktop unit that I have in my office as a single node that has 8 processors. Now, the login nodes are a dedicated set of computers where everybody who logs into the system initially lands. This means there could be a pretty large number of users sharing the resources available on those nodes, and so it's not a good idea to do large-scale computing there. Big analyses could outconsume resources like RAM that are available on those login nodes, and that could impact all the other users. In a lot of cases, limits will be set on things like RAM usage per user and runtime for individual computational tasks on the login node to help keep problems from arising. Simply, large analyses are not what the login nodes are intended for. Instead, they're for doing things like organizing your files and writing and editing scripts that will define compute jobs, which we'll talk about next. The compute cluster represents the real strength of the supercomputer, and it's the part where you'll do most of your computing. What I have represented here is the Owens compute cluster at OSC, which consists of a set of nodes all linked together to form what has the capacity to work as one big supercomputer. Specifically, it consists of 808 compute nodes that are categorized as standard compute nodes. And these each have a total of 28 cores or processors and 128 gigabytes of RAM, which means there's around 4.5 gigs of RAM per core. So in all, this means in total, there are over 22,000 processors available on the standard nodes of that system. Then on top of that, there's an additional set of nodes that are called high memory nodes. There are 16 of these, each contain 48 processors, and have 1.5 terabytes of RAM. These can be explicitly requested if you have computing tasks that require more RAM than the standard nodes have available. So adding up both the standard and high memory nodes, the compute cluster of the Owens supercomputer offers a total of comfortably over 23,000 processors. At this point, we've looked at 2 of the 3 main components. The first, the login node, can be thought of as a staging area. It's where you first land when you log on, and where you can do basic work requiring minimal computation. The second is the compute cluster, which is where you'll send your big compute jobs. The third is the data storage part of the system. We'll consider it as 3 sections. You can think of each of these as something like an external hard drive you'd plug into your own computer to store data on. The first is the user's drive. As soon as you get an account set up with OSC, a folder is created for you on this user's drive that allows you to store up to 500 gigabytes of data, or 1,000,000 files, whichever comes first. These are hard limits that can't be extended. A second drive is called the project drive. Projects can be set up, and each will have a folder on this project drive. There's more flexibility with this drive in terms of storage thresholds, and users can request that specific amounts of storage be allocated to their project. Note that as of July 1st, 2020, charges are accrued for storage space allocated to users in this location. The owner of a project can provide access to any other OSC users they choose. The third storage drive at OSC is what's referred to as scratch space. This has the advantage that it's unlimited. You can store as much as you need there, and no charges accrue. The downsides are that unlike the users and project drives, which are consistently backed up, data on Scratch are not backed up, and Scratch storage is meant to be temporary. Files that aren't modified within a certain amount of time, say a few months, are automatically deleted. Each of these 3 drives, Users, Project, and Scratch, are always available, and your folders on those drives can always be accessed from either the login or compute nodes. Finally, I should say that what we've just looked at is Owens, which is actually just one of 3 independent supercomputers at OSC. The other one you're likely to encounter is Pitzer, which is a separate system that's structured in a very similar way. In fact, each of the supercomputers there share the same storage drives. The only real difference in Pitzer is in the size of the compute cluster. You can access Pitzer simply by replacing owens.osc.edu with pitzer.osc.edu in the host name when you log in with SSH. And beyond that, for most usage, you'll likely encounter few or no differences in the two. The most likely would relate to software that's available, and we'll talk more about software in a future video. Hopefully that gives you a better sense of how the Ohio Supercomputer Center is structured, and by extension, maybe some other high-performance computing systems you'll find yourself using. In the next video, we'll talk about sending compute jobs from the login node to the compute node.